All right. Hi. Can you all see this on Canvas? Is that available to you guys? Yeah. All right. Before we start, are there any questions about your final exam? How many questions it is? How long you have? Anything like that? I believe it's 20. I'm not entirely sure on that, but around 20.
My line pass says it's in Willard 75, but then on Canvas it says it's like on the second floor of Willard. Do you know which room it's actually in?
I can message Dr. Lori to get an answer on that, but I'm not entirely sure on where it's actually at, if it has two different locations. Does everyone see that? Two different locations?
I didn't check mine.
Okay. Because, yeah, I get told the location when I get there tomorrow morning. I get handed the exams and they tell me where to go. So I won't know until tomorrow morning, but I can message Dr. Lori and figure out where it is. Right. Any other questions? Yeah.
How much of it is old material and how much of it is like new material?
So it's based off lecture content. It's if it's like this many lectures was dedicated to this topic, that's how many points it gets on the exam. So I would say a good chunk of it is new material because it's been a while since the last exam, but it's also a good chunk of old material. Yeah, it's a lot of material, but it's not too aggressive in it, I think, at least like from my perspective. Any other questions? Alrighty, let's start then. So this first question, it's a symmetry question. They give us trans 1,2-difluoroethylene. And in this, they just want us to identify the 4 different symmetry operations. So what's the first one we should always identify when we're doing this? E, identity. That's a free one. Always identify it. You don't have to do anything to draw it. It's just, that's what it is. Does this have any rotation axes that I can rotate it about? Where? Yeah, out of the page. And what's my C rotation? C2. So if I have out of the page, it's kind of hard to illustrate this one. I can rotate it around that for a C2 rotation. You can also draw it just like rotating that way if it makes it easier in your head. But the plane is coming out of the page towards us. And that's the only C2 it has. It doesn't have any perpendicular ones because if we rotate it perpendicular to that double bond, we're going to flip where our fluorines are, and we don't want that. If we rotate it along our double bond, we also flip where our fluorines are, and that's not the same. All right. What's another one that you guys can see? Is there a reflection plane anywhere? Following our chart, we would first look at a horizontal reflection plane. Do we see a horizontal one that would be perpendicular to our rotation, our rotation? Yeah, there is. So we have a sigma H. This one is just in the plane of our paper. That was a really bad box. So this is our sigma H. It's just a reflection plane. And then does anyone have an idea of what the last one could be? Yeah, it's an inversion point. So to draw the inversion point, I don't think there's really a right way to draw it. Usually I indicate where the inversion is happening and then I draw like a little arrow. So in this one, our inversion point is right in the middle. So what happens to this fluorine? It ends up over here. And this fluorine ends up here. And then same thing with our carbons, or sorry, our hydrogens. They flip. And this is our inversion. Any questions on these symmetry operations? There are more that we need to know about, but this is just a quick example of 4 of them. So now that we've identified the symmetry operations, we can go ahead and try to assign the point group of it. I don't have the chart here, but the chart will be given on your data sheet. You don't need to memorize it, and it will be the one that you are used to, not the one that you have seen in class sometimes from the old exams. So if we follow our chart, what do we get for this one? Yeah, go ahead.
C2H.
Yeah, C2H. So it's not linear, and then we do have a rotation axis, but we don't have a perpendicular C2 or greater rotation axis, so we go to no, and then it asks us about a reflection plane, a horizontal one, and we go yes there. right, any questions on symmetry and point groups? Cool beans. All right, a triatomic molecule. So this one is FHF-. It's an example of one of the ones that we did in class. It looks intimidating at first, but I promise it's not that intimidating. It's a really simple one because when you break down what you're really looking at, you only end up with one bonding and one antibonding orbital. So here they give us our two F atoms and one H atom. They give us all our basis sets already. So now we just need to think about what's going to happen. Do you think our 2s is high enough in energy to interact with our 1s? No, so these are going to be non-bonding orbitals, meaning that they're just going to stay around the same energy. And up here it says that they're all degenerate, meaning all 6 of these lines are technically the same energy. They're just drawn this way because there's not enough space. But when we draw our molecular orbital diagram, they will be drawn at the correct energies. So which one do you think is going to be lower in energy? The one with the 2 same shaded circles or the one with the 1 shaded circle different? Yeah, same shaded. So we're going to get 1 lower in energy and then 1 just a little bit higher in energy. And these again are non-bonding orbitals. If we're looking to assign them U, G's, and sigmas, we can assign them a sigma U up here and a sigma G up here, but there is no star or no star, I guess, because they're non-bonding. They're not going to impact our bond order, and they're not interacting with our H molecule. So now we need to look at our 6 basis sets for our fluorines and see which ones are going to interact with our hydrogen. Do we think either one of the first 2 in the column are going to interact with our hydrogen? Are they in the same orientation to interact with it? No, they're not. We have to have them on the same axis, right? It's the same as if we had 2 hydrogens and like a beryllium. They need to be aligned. So these first 2 are going to be non-bonding orbitals here. Now we go to the next 2. Do you think our hydrogen atom is going to interact with these 2? Are they aligned on the same axis? No, it's not. So these 2 are also non-bonding orbitals. Now what about these 2? If we look at this one down here, what if I had the hydrogen in the same phase as my 2 p orbitals? Is that going to stabilize this interaction or destabilize it? It's going to stabilize it because they're all in the same phase. So we get one orbital much lower in energy. So this one's going to go way down here. And this orbital represents if I have my 2p orbitals in the same phase as my 1s orbital. Another way that you could draw this is either one of these representations. It's the same thing. It's just showing that we have some type of interaction between these 2p orbitals and our 1s of our hydrogen, which means that we also have an antibonding orbital that corresponds with this when our hydrogen is out of phase with our 2p orbitals. So our higher energy orbital then would be you can also draw this one squished up. That's the other way, but I'm not good at drawing those, so I'm not going to draw it that way. We still don't have enough orbitals in the middle here. We haven't looked at this one right here. So this one is going to be slightly higher in energy because when we put something in the middle, or it doesn't matter what phase when we have something in the middle, it's always going to have one node. If our hydrogen's in phase, there's a node. If our hydrogen's out of phase, there's a node. So it goes up in energy, but it's still below our 1s in energy. So now we're going to just connect where they belong. Our bonding orbitals are going to go both to our fluorines and to our hydrogen, as well as our antibonding. And then the rest are just because of our fluorines. Now all these orbitals in the middle are the same thing as these orbitals over here. So you could redraw them if you'd like, but you don't have to for this example. They're the exact same because it doesn't matter if our hydrogen's in phase or out of phase. You would draw them with the dot in the middle. Joe, do you have a question? Which one? Sorry. The 4, so that's going to be this set right here, because no matter what phase I put my hydrogen in, I'm always going to have one node. So if I have it not shaded, I have one node on this side. And then if I have it shaded, I have one node on this side, but it's not truly a bonding. So now if we go to label these, again, they usually are labeled with symmetry operations, so like A1G, B1G, B3U. So we'll try to simplify them here, where down here typically is AG. Here we'll just call it sigma G. Up here we have non-bonding orbitals, and these are just U. I guess you can call them pi U if you really wanted to. Same thing up here. And then up here would also be AG star, but for simplicity, we'll call it sigma G star. And the last thing we have to do is just fill in our electrons. So this is FHF minus. So I'm just going to throw the extra electron onto R1s. And then I'm going to fill in these like they're two separate fluorines. Then in the middle, we should have 16 electrons. So we'll do a different color. And there we go. So I'll mark that these orbitals are the ones that go up here. This one is going down here and up here, and then the other 4 are the ones that are the 4 in the middle. Any questions about this ML? I would say this is a little bit harder than what we would expect you to do because the naming mechanisms don't really work out, and there's a lot of electrons to think about. But at the end of the day, there's only 2 orbitals that you're really interacting, and that's that AG one all the way at the bottom, and then our AG star all the way at the top. So our antibonding and bonding ones. Yes. Yes.
Would that also get attached to the 1s because it's like the 2
It technically doesn't count as a bonding interaction, but you could if you wanted to. I don't think I'd take off points if I saw someone drawing an interaction there. But stereotypically, it's not drawn there because it's not really an interaction. It's just slightly higher in energy because there is some anti-bonding characteristic to it, but there is not very high bonding characteristic to it. Any questions on this? The last part just asked to calculate the bond order. So when we're calculating the bond order, remember we're only looking at bonding and anti-bonding orbitals. All the non-bonding orbitals we don't care about. So here we only have 1 bonding orbital and 1 anti-bonding orbital, and our bonding orbital has 2 electrons, our anti-bonding has 0, so it would be 2 minus 0 divided by 2, and that gives us a bond order of 1. Any questions? All right, let's talk about some rocks. So here's pyrite. We discussed it a little bit in class. It has a very similar crystal structure to sodium, but it's not the exact same. It's slightly different because it's an FeS2 rather than a 1-to-1. It's a 1-to-2 ratio. So the first question is asking us for the coordination number of iron. Iron are the blue dots here. What do we think it is? I think it's easiest if you look at either this top or this bottom one, either one circle, to figure out the coordination number of it. You can use your fingers if you want. You don't have to say it out loud. It's 6. So yeah, each each sulfur group is considered one atom that it's bonded to because it's bonded to like both of them at the same time, kind of like when you illustrate a carbon-carbon bond to a metal.
So if there were like 3, it would still be.
Yes, yeah. If they're all drawn in that one little lattice point, then it's considered like 1. So yeah, it's going to be a coordination number of 6. It has an octahedral coordination. So next, it asks us about fractional coordinates. Does anyone remember the fractional coordinates and how we find them? What's our origin point? Yeah, the dot closest to us. So this is going to be our origin point. And if I draw an axis, or axes, z is up, y is back, x is all the way to the right, and a whole cell is 1. So if a whole cell is 1, for the first step, we're going how much to the right? 1/2, so that would be our x coordinate. So we're immediately going to remove those 2 options, and then we're going to go back. And how much do we go back? 1/2 as well, and we don't go up at all, so it has to be b. Does that make sense? How do you feel about fractional coordinates? Good? Okay. Another unit cell question. So magnesium silicide is a semiconductor. It's just Mg2+ and silicone in it. We are given the unit cell, and they just want us to ask some or answer some questions. So the first one it's asking is, what is the packing atom? What do we think it is here? What do we think the packing atom means? Let's start there, maybe. Is it the one that fills the hole, or the one that has the like FCC, HCP, BCC structure? Can't hear. Those are the filling atoms. So what do we think the packing atoms are? The ones that are in the FCC or the CCP or HCP, you know, the packing atoms, they have packing in their name. So here it's asking the packing atom. Which one here is the packing atom then? Which one is it in the holes? Magnesium, yeah. And what type of structure is magnesium in? FCC, yeah. It wants us now to draw the 2-dimensional projection. So these are when you have your z equals this height, and you draw a little square, and then draw each layer of it. So we'll start off with z equals 0 and 1, because those are the easiest to illustrate. So z equals 1 and 0, we're looking at this layer down here, and this layer up here. So we're just going to draw what that looks like on a 2D projection. So we'll have a magnesium on each corner, and then 1 in the center. And then down here, I'll just write Mg2+. So that's our top and our bottom layer. So now we're going to go to the next layer. The next layer is this one right here, and it's the exact same as this one up here. So both these layers are going to get the same illustration. And right here we'll write z equals 1/4 and 3/4. And then we'll add in our silicone. And then we have one more layer, which is this middle layer right here of magnesium. And this layer of magnesium has them on the edges. And this will be z equals 1/2. Do you think you can do this on the exam? Can you draw 2-dimensional projections? Are there any questions about this? Yeah. I think just the atom is fine. It's just because if you're writing in like pen, you're probably doing shaded and unshaded. So just like, show which one, or pencil, show which one you mean is what. But I don't think the oxidation state matters unless it explicitly states it.
So like just Mg and like Si.
Yeah, I think that's fine. So now it's asking us what type of holes are filled. So we already stated that silicone's in the holes. What type of holes are silicone filling here? Well, let's look at this top one and draw some connections. So if I'm looking at this silicone here, it can bond to that magnesium, that one, and that one. Yeah, they're tetrahedral holes. And how many silicones do I have in here? In my cell? 8. So how many tetrahedral holes do you think are filled? 8. And that's the max tetrahedral holes you can have filled in an FCC-like structure. So we have 8 tetrahedral holes. When we're talking about interstitial holes, the most that we can have of octahedrals in like an FCC, BCC, HCP, well, technically an FCC. Well, in an FCC structure is 4 octahedral holes and 8 tetrahedral holes. So now, looking at magnesium silicide, what type of semiconductor do we think this is? For something to be doped, what did we say it has to be? The second constituent, or whatever constituent we're adding to it, is such a small amount compared to the first. It's when we have that 1 minus x, where x is much, much smaller than 1. So does that fall into that category? No. So for the sake of this course, this will be considered undoped. But the interstitial holes is like one of the last things that we talked about, where you're filling in vacancies. So we either have something that's filling in the holes or a cation vacancy. So like one thing is changing out that interstitial hole, just one of them. Does that make sense? We talked about it very, very briefly. I think it was one slide at the end of, yeah, I think the interstitial holes slides. Right. Any other questions on this? Cool. So now we're going to talk a little bit about periodic trends. Here it tells us that zirconium and hafnium have similar atomic and ionic radii, but differ in their atomic masses and electron counts. So does anyone have an idea why this might be? Well, why don't we look at the periodic table then? So if I'm looking at zirconium, zirconium's here, hafnium's right below it. What happens in between these two things, these two rows? We added a lot of electrons, so why don't we look at their electron configurations? Maybe that'll tell us something. So for zirconium, we're going to have an electron configuration of krypton, 5s2, 4d2. And we'll see a similar electron configuration for hafnium, but instead, we'll notice that we have the addition of f electrons. So what do you think the addition of f electrons does? Does anyone remember what group gets added there? I think I heard someone say it. Let's look back up. So here in the periodic table, there's a little star. Why do you think that is? What group gets added? The lanthanodes. So what we're seeing is when we have the lanthanides, this introduces a new block, a new subshell, the f orbital. And this f orbital is very poorly shielded, even though we have an increasing nuclear or effective nuclear charge. This phenomena is known as the lanthanide contraction. So what we'll see is these heavier elements, even though they have larger effective nuclear charges, their sizes are smaller than expected. So I'll write that all down because that was a lot of words to say. I'll give you guys a second to write that down. Any questions on this? All right. Are we ready to move on to the next one? Cool. So the next one tells us oxygen has a smaller first ionization energy than nitrogen, even though oxygen's valence electrons experience a larger effective nuclear charge. So does anyone have an idea why this might be? Yeah. Yeah, so if we look at oxygen's electron configuration, I would have 1, 2, this is my 2s, this is my 2p, and I have 4 electrons in my 2p. But if I look at nitrogen's electron configuration, I have 3 electrons in my 2p. So when I'm ionizing something, I'm removing one of those electrons. When I do that with nitrogen, I'm removing that 3rd electron, and I'm going from a half-filled subshell to less than a half-filled subshell. That takes a lot of energy. But when I do it for oxygen, I'm removing an electron that's paired up. And what happens when we're pairing up electrons? Is that an easy thing to do? It takes pairing energy. There's mutual repulsion existing between our electrons. So by ionizing it, we're relieving that. It doesn't have a high ionization energy, or I guess a low ionization energy, but it has a lower one than that of nitrogen, even though the expected trend is for it to be higher. So again, I'll write that into words because that was a lot to say. Any questions on that one? How do you feel about periodic trends, effective nuclear charge? Good? All right, some more of the new stuff. So talking about materials and density of states. Here they tell us to draw the diagram. If you need me to scroll up too, if I'm going too fast, please just let me know. Here they want us to draw the density of states diagrams for gold and silicon. So what type of material is gold? A metal. So is it a conductor, a semiconductor, or an insulator? Conductor. Awesome. What about silicone? Semiconductor. Yeah, it's a semiconductor. So first we'll draw gold. And there's a lot of different ways to draw density of states. I'm just going to draw them the way that you guys have seen them in class, which are the band diagrams, or I guess the energy versus DOS diagrams. So energy would be this axis, and then DOS is our density of states on our x-axis. So for a metal, we usually have a filled S, so that's what we're seeing down here. And then what we really care about is this middle band, and in the middle of this band would be our Fermi energy. And how filled is this band? Do I go above the dotted line? Below, yeah. It goes right up to that dotted line. And then technically there's a band above it as well. but this would be for gold. It is a conductor. Do I need to include a band gap here? Nah, there is no band gap. The electrons can easily transfer over that line. Now for silicone, we said this is a semiconductor, so its density of states looks slightly different. So we would have a filled band down below. And where does my Fermi energy go here? Does it go between my two bands, in between a certain band? Yeah, between. So our E of F would be here. And now does this have a band gap? Yeah, it does. The electrons need to transfer all the way up there, so it has an E gap. And since we said this is a semiconductor, what is the size of that band gap? Yeah, so it's a semiconductor, so our E gap is going to be less than 3 electron volts. Now, when we're looking at both of these materials, which one do we think is going to be a better conductor? The one that's a conductor or the one that's a semiconductor? The one that's a conductor, I love that. So yeah, our gold is going to be a better conductor. Because it's metal. Metallic conductor with no band gap. And then, like we said, silicone is a semiconductor, so while it can conduct, there is an energy cost to promote that electron over that band gap. Now, if you were asked about insulators, how would that differ from your semiconductor drawing? Yeah. Yeah. So if you were asked about insulators, it's going to look almost the exact same as your semiconductor, but instead you would say your E gap is now larger than your 3 electron volts. And this is a semiconductor. How do we feel about, yeah. It's just one of those materials. We discussed it a lot in class, so I don't think it's going to be like a pop quiz. Like, you have to know these materials are semiconductors, but it's a pretty well-known semiconductor in like electronics and stuff like that.
Obviously, like, it would be beneficial, like how they do, like, these, like, name, like, both the exercise, like, the exercise.
Yeah. Like, I wouldn't say memorize the materials, right? But there are certain things that we've talked about a lot, like tin can be a semiconductor or not a semiconductor, and we spent a lot of time talking about the P block, especially group 4 elements, because of their strange properties and how, like, carbon allotropes can range from insulators all the way to conductors. So again, I wouldn't say memorize it, but like if we asked you diamond, like on the other practice exam, that's one of the things that we would expect that you would know as an insulator compared to graphite, which is a semiconductor, or arguably, call it a semiconductor.
Would the graph change much between semiconductor and insulator?
No. The only thing that you would need to specify is that band gap, because that's the biggest difference. Is one has a very large band gap, and we should know about the range of how large that band gap is, more than 3 electron volts, because we're trying to think about the bond association energy, and that's usually around 300 kilojoules per mole-ish. Any other questions on that? Cool. All right. So now we're going to talk a little bit about colors and some more semiconductors. This is really just a math problem. So on your data sheet, you should have this formula. It is 1240. Sorry, that is not a 4. Divided by lambda equals energy, and this is lambda in nanometers. You don't need to do any converting. And this is energy in electron volts. You don't need to do any converting. So since they gave us energy and they want us to figure out what color it's appearing, we're going to figure out what color it absorbs and then work backwards from there, looking at its complementary and all the colors that are underneath that. So if we're starting off, we're going to just rearrange this formula a little bit. So if we do 1240 divided by our energy, that'll give us the wavelength of the color absorbed. Again, that is not the color that it's going to appear, but it'll tell us what color it'll appear. So for the first one, we have this iron oxide. It'd be 1240 divided by 2.2. And this gives me 564 nanometers. So what color do we think this is going to appear? I don't have a color wheel on me. Maybe I do. I probably do. Maybe I don't. I lied, I don't. Usually I do. Yeah. Is that the color it's absorbing or appearing? Appearing.
564.
We have to take the composite of all the color values. So if I look at that range, where does that go into the middle to then? Orange. Do I have a color wheel on here anywhere? Let's see if I can show that. Give me 1 second. I think I do have a color wheel somewhere on my computer. All right. All right. Color wheel. So if we have 564, we're right around here. So that means we're absorbing all of this. We're going to go to the middle of this range. Orange. That's it. I'll come back to this as we do the rest of the problems. I see. Oh. It oftentimes does fall under that, but a lot of the times it also doesn't. This is the true way that it's doing it. So typically when we're looking at things, they absorb over a range rather than just a singular wavelength. So that's why we're incorporating this whole range. We're assuming that it's absorbing everything in it below. We'll continue. We have 4 more examples to do this with. Don't worry, we'll figure this out. So the next one, it's titanium dioxide. This would be 3 volts, and this gives us a 413 nanometer. So if I go back to my color wheel, 413 is really low. It's actually in the UV region. This doesn't show it right because this doesn't have the full length on it. So 413 is one of the ones that we consider white. I think a yellow answer would also be okay, but white is the true color of titanium dioxide. And that's because it doesn't absorb visible light. Next, we have gallium arsenide. So this would be 1240 divided by 1.4, and this gives us 886 nanometers. So if we go back, 886 is way off. It absorbs all colors of light. So if it absorbs all colors of light, what color do we see? Black. And that is the answer, but I'll go through the other two just so we can have a little bit more practice with this. So next we have this silver iodide, and this would be 442. So if I go back, 442 is right around here, so it's absorbing this region. So this is going to be like an orange yellowish color. And then the last one that we have is cadmium sulfide. So 1240 divided by 2.6, and that's 477 nanometers. So similarly, we'll go back and take a look at it. And 447 is right around here. So our middle, pretty yellow. It's a pretty yellow compound. Any questions about that? Yes.
Can you go over
white. So it's, I think we should probably lower that electron volt range because it's a little bit confusing. It's such a low wavelength that it's not really purple. It's UV wavelength at that point. I would also use like a little bit of logic here. We know titanium dioxide's white, right? Like we talked about this when we were talking about colors and splitting and all that fun stuff. But if it's really low wavelength, I would say 415 and below, just assume that it's UV.
Okay, so if it's in like where it's like super purple,
Yeah.
assume that it's gonna be like
Same thing, like really, really high, assume that it's absorbing all color at that point.
okay, that makes sense.
Just so I can picture how this works, can you give an example as to something that would be green?
Green, yeah, let's look at the color wheel. Green, something that is strictly red.
Where's the example?
Something that is absorbing strictly red. So there are things that absorb strictly red, but when we're talking about semiconductors, that's not the case. So the whole point of semiconductors is they can absorb a wide range of colors, right? So it's different from other color theory. It's also true that sometimes, yes, it is the complementary color, but we also have to take into regards the whole spectrum when we're thinking about semiconductors. Yes, Joe?
If something is absorbed strictly red, then wouldn't it absorb everything else?
If it's just red, like not a semiconductor, if it's just a red absorbing compound. So, yes, semiconductors, it would absorb the whole range.
So semiconductors should be basically just like find wherever its wavelength is on the circle and go
To the lower wavelength.
counterclockwise
Yes.
around it and then draw a line.
Yeah, so like if it tells you it's 650, I would draw something like that, and then I'd look for the middle of that somewhere around here. Any other questions on that one? I know this one's a little bit funky with the theory. Just do your best. There's only a few semiconductors that we've talked about in this class anyways, and there's only a few that we know the band gaps of, so do your best. Any other questions? Okay. So the next one's just identifying the oxidation state, the d electron count, the molecular shape, and then drawing the d splitting based off the molecular shape that we found. So for the first one, they give us K2NiCl4. So what's the charge of my individual complex there if I remove the counter ions? What are my counter ions here? Anything outside the brackets are counter ions. They're put there to balance out our charge. So here I have 2 potassiums here. Each potassium has a +1 charge. So what is the charge of my complex then? 2 minus. So I have this NiCl4, 2 minus. What's the charge of a chlorine ligand? And I have 4 of them, so -4. So what does nickel need to be so my complex is -2? Yeah, so we figured out our oxidation state. Nickel is +2. Now we're going to figure out our d electron count. If I look at nickel's electron configuration, it's argon 3d8, 4s2. If it's 2+, which electrons am I removing, my s or my d first? My s electrons, they stick out further, they have a higher quantum number, they're easier to remove. So this means my electron configuration is just 3d8, so I have 8 d electrons. And what shape do we think this is going to undergo? Before we get there, we're going to talk a little bit about the complex and what we know about it. So far, we know it's D8. We know it has a coordination number of 4 because there's only 4 ligands there. Remember, anything outside the brackets, we don't care about. That's not bonded to a metal that is there to counterbalance the charges. And what type of ligand is Cl-? Yeah, it's a weak field ligand. So all this tells us a lot. We know that we talked about 2 different types of structures that can be coordination number of 4. We have square planar and we have tetrahedral. Which ones prefer weak field ligands? D8 weak field ligands, to be explicit. If I ask which one's preferred strong field ligands, is that easier? It's going to be tetrahedral for our weak field ligands. They want to balance out the charges, they spread them apart more. So what we have is this tetrahedral shape. So what does the tetrahedral diagram look like? The MO diagram, I should have been more explicit about that. Yeah, we just flipped our octahedral. So now we get 2 and 3. And even though this is D8, so it's not really going to matter high spin or low spin, what spin are tetrahedral compounds always? High spin. Oh, I'll write that here. But D8 doesn't matter. It doesn't matter if you fill it in high spin or low spin. It's the exact same. All right, the next one gives us a nickel cyano complex that also has counter ions. So what's the charge of this complex? You can use your fingers, you don't have to say it out loud. If I remove my counter ions, what was that? 2 minus. Yeah. No, you're good. So yeah, it's 2 minus because we have potassium here, which both contribute a +1 charge. So my actual complex then has a 2 minus charge. Now, what's the charge of a cyanide ligand? -1. So what does my nickel need to be to get a -2 complex? +2. Wow, it's the same oxidation state. So we already know the d electron count. Now we just need to think about the structure of it. So we still have a coordination number of 4 and D8, but now we have a very strong field ligand. So what structure do you think this one's gonna take? What was that? Yeah, square planar.
I think D8 was always square planar.
Not always square planar, it depends on the strength of your ligand. And what type of metal you have. So if you have 4D and 5D metals, they always adhere to one type of structure. So that's our square planar. Now what if I had nickel CN6? What structure is that? It has a coordination number of 6. And how does my octahedral splitting look? Yeah, the opposite way. So we have a triply degenerate at the bottom, doubly degenerate at the top. I think those are the 3 that we talked about in this class, right? Cool. And where does high spin and low spin matter for octahedral complexes, or I guess all complexes? What is that range? Does D1 matter? Can D1 be high spin or low spin? D2? D4 through? D7. D8 is one of the ones that it's it stops mattering at D8. But D4 through D7 are the ones that have high spin and low spin states. Remember, high spin states are because we have a, a small delta O, large pairing energy, and we'll talk a little bit more about that in a later problem, actually. All right, another problem. So here they give us 2 formation constants, and they want us to rationalize why one is much larger than the other. So what is cyanide? What type of ligand is that? It is a strong field. If I asked you to identify it as hard, soft, what would you say? We bond through a carbon, a negatively charged carbon. Soft. Positively charged carbons are harder. That's how I like to think about it. And negatively charged carbons are usually softer. But anyways, so cyanide is a soft base. What about chlorine? Chlorine is also a soft base. It's not as soft as cyanide, but it is a soft base. These are both soft bases, and gold is also a soft base, but cyanide is softer than chlorine is. So Cn minus is softer than Cl minus. So it bonds better to the soft acid Au plus. So if we have a higher Kf, this usually means that we have more products. Additionally, like someone said, cyanide is a strong field ligand. So it can pi back bond to our gold, and that's a much more stable interaction. Yes?
How do you know it's softer?
Trends, and I mean, I know they're softer because I work with them, but they're trends. So usually cyanide, chlorine, they're softer, but as we become larger, they become harder. Or did I say that backwards? I might have said that backwards. But chlorine, if you said chlorine is moderate or harder in this scenario, I don't think I would take off points as long as you can recognize that cyanide is softer than chlorine. Yes.
So the lower halogens are softer, right? Because they still have the same charge density, but they're much lighter.
Yes. Yeah.
I mean, not the same charge.
Yes.
The
Yeah.
same charge. Okay.
So just look at the trends. Typically when we're talking about them, it's a much more obvious example, but in this one, using the formation constants, you would say, well, cyanide, softer or stronger field ligand, can bond better than gold. Chlorine, moderate field ligand or soft ligand, whatever you want to call it. But I would say it's kind of like the spectrochemical series where it's a scale, like it's in relation to each other a lot of the time. So I wouldn't dock off points if someone said moderate or hard in this case for chlorine, as long as they establish that cyanide is softer. Does that make sense? Because I don't want it to be about memorization. I want it to be more about like reason it out with the information you know and the information you're given.
Well, can that always be higher than softer?
Yeah, because it's going to well, not if it's softer, if it's a favorable interaction. So like since this is gold plus and cyanide, it's going to have a very, very high formation constant because they're both soft, well, one's a soft acid, one's a soft base, and one bonds really well to the metal center. So chlorine only has sigma donation, while cyanide can do pi acceptance and sigma donation. Does that make sense? Okay. Lewis structures, because we haven't forgotten about these. This is going to be the N minus V method. So this is xenon dichloride. It's actually one of the only known stable xenon chloride molecules. So here, the first thing that we're going to do is figure out the needed electrons, the valence electrons, the bonded, and the lone pair. So how many needed electrons do I have to have for this 3-molecule structure? How many do they each want? 8, and I have 3 of them. 24. Now, how many valence electrons do I actually have? Xenon has 8. What about my chlorines? 22. So to figure out how many bonds I have, I do N minus V, and that gives me a number of 2, but there's 2 electrons per bond, so I have 1 bond. And then I look at my remaining electrons from my valence. So I took away 2 electrons to form my bond. So I have 20 remaining electrons, which means I can have 10 sets of lone pairs. So 24 minus 22 equals 2. And that gives me my bonds, but 2 electrons per bond. And then 22 minus 2 equals 10, 20. And this gives me my electrons, but I have 2 electrons per lone pair. So now I'm just going to draw the resonance structures that coordinate to these. Which one is my central molecule here? Xenon. And I have 1 bond, so whichever one you want to start off with, it doesn't matter. I'm going to start filling in my electrons. I wrote 2 different things here. It doesn't matter. Both of them are going to have the same count. I did Cl already, so we'll do Cl. I think on this key I have F, so you'll get 2 different examples. But they're both the exact same amount of valence electrons. Doesn't change. Xenon difluoride is a fluorinating agent, if you wanted to know about that. Different from xenon dichloride. Xenon dichloride doesn't have many good uses. It's just kind of, we made it. What charge does xenon have in this case? Yeah, plus. It's a noble gas. It has a bond. It usually doesn't have a bond. Resonance arrows are double-sided arrows like this. They are not equilibrium arrows. Equilibrium arrows are these arrows. That is different. This is a resonance arrow. That's more of a just like a nitpicky thing. You won't get any points taken off if you don't draw the right arrow. So now we're just going to draw the other resonance structure where we move our bond. Minus and plus. These resonance structures look good? Can anyone think of another one? No. Next, we're going to draw the composite structure. So that means we're going to combine these two. And the way I usually like to think of this is like a table. So if I look at my first chlorine, the one on the left, in that scenario, I have a single bond. But in the one on the right, I have a 0 bond. So I know the overall bond order for that is 1/2. But I know more importantly, I'm going to have a dashed line representing each of my chlorines. So I would start off with xenon, and both of these are going to have a dashed line to represent they're somewhere between a single bond and a no bond. I'm also going to include my alone pairs. In both examples, my xenon has 3 sets of lone pairs. So in this example, it's also going to have 3 sets. But when I'm drawing my lone pairs, how should I draw these? Are they all in the same plane? No, there's some symmetry to them. So I'll have a lone pair here of one sticking out. Then I'll have one facing the back. Now, what about my chlorines? What are my formal charges on them? In one of my structures, it's -1, and the other structure, it's 0. So what's the average of that? -1/2. And then how about my xenon? In both structures, it's +1, so the average of that is? Yeah. All right, any questions on the composite structure? You could also draw dashed lines in A if you wanted to. That's acceptable, like instead of the full bond. You wouldn't lose any points for that. So the next problem asks us about the geometries. We discussed 2 different types of geometries in this class. Electronic geometry, which is based on the number of electron groups, where there is no discrimination between lone pairs and bonds, and molecular geometry, which does take into account how lone pairs affect the angles. So in the first one, we're looking at the electronic geometry. So every time I think about electronic geometry, I think everything is the same, right? It doesn't matter what electron group domain I have. There are 5 different electron group domains. We didn't explicitly discuss those in class, but in this case, we have bonds and lone pairs. So I have 5 domains here. I have 3 sets of lone pairs, and I have 2 bonds, right, to my central xenon. So if I have 5 domains, what electron group geometry is this? What's the shape of 5? That's a question I never thought I would ask. Does anyone know the abbreviation for it, maybe? Yeah, there we go. So this means that we're just taking into account everything that surrounds our xenon. We're not discriminating against our lone pairs. Now, our molecular geometry, we're going to take into account our lone pairs, but we're going to take into account the repulsion they cause. So if I have lone pairs surrounding my central xenon, what do you think that's going to cause to the shape of my molecule? Are they all going to balance out? If I have 3 of them surrounding my central xenon. Yeah, they are. So we're just going to have a linear molecular geometry. Any questions on that one? I like this one. I think this one's a fun question. Does this, I answered this question already, but I'm going to ask it again. Does this molecule experience no bond resonance? Lovely. Great job. All right, some electrochemistry. Oh, yeah.
So when you're looking at like the electron domain geometry, you look at the composite structure.
Yes.
So like
That's why I said it has 5 electron domains.
even though it doesn't exist like that.
Well, it does exist like that. When we're actually looking at this molecule, we wouldn't be able to tell the difference between those two chlorines. That's why we draw them as these like no bond resonance structures, because we don't know the difference. We just know sometimes they're bonded, sometimes they're not. But every time we're asking about electron group geometry or molecular geometry with these, always the composite structure. Yes.
So are all 3 electron pairs like spaced out evenly? That's why it's linear?
Yeah, so they're all surrounding the central. I don't have like a third arm, so I don't know how to do this, but like 2 are there and then like 1's back there, right? Like if I am the xenon, with that, right?
Okay.
Going off of that question, so whenever you have like lone pairs on your like center thing, right, always gonna have like opposite stereochemistry.
Yeah, because they have repulsions. They're kind of similar to ligands, but like they have very noticeable repulsions because they're negatively charged. So you want to make sure that they're on like that axis and they're all spread out. You don't want to put them up and down because that isn't the best distribution of charge for your molecule. Anything else? All right, electrochemistry. So there's a lot of different types of electrochemistry questions. I'm a fan of the Latimer diagrams, which is why you'll probably see them a lot from me. But we're going to do a Latimer diagram. Don't forget there's Corbeau diagrams and Frost diagrams. So please also study those and remember the math that you need to calculate the electron or the charge of it. For now, this is just asking to write a balanced equation based off our Latimer diagram. So looking at it, it wants the reduction. So if it's asking for reduction, that means we're reading it left to right because this is showing us the reduction of vanadium hydroxide to vanadium solid. We can tell that because we're going from a +5 oxidation state to 0. So if we decrease oxidation state, that means reduction is occurring. If it was asking for oxidation, we go the other way and we flip the signs. So here it's just asking for VO2. So we're going from this state to this state. And every time you're writing an oxidation, reduction reaction, it's always going to follow the same steps. So first you want to balance any atoms that aren't oxygen or hydrogen. So here we're going to look at our vanadiums, and they're both 1-to-1 already, so we don't need to do anything. Next, we're going to balance our water or our oxygens with waters. So how many waters do I need to add to my product side to balance out my oxygens? 1. Third step, we're going to add hydrogens to balance out our hydrogens on our product side. So how many hydrogens do I need on my reactant side? 2. And now we're mass balanced, but we're not charge balanced. So that means everything here has the same mass on our reactants and products, but we have different charges on both sides. So looking at my products, I have a charge of 0 because water is neutral and so is vanadium solid. But looking at my reactant side, I have a charge of +4 because I have 2 H pluses and a VO or a vanadium oxide with a +2 charge. So how many electrons would I need to add to balance out these charges? 4. And it's always going to be these exact same steps. If this was in basic conditions, you would add one more step where you add hydroxide at the very end. Yes. Sorry, that's electrons, not H+. There you go.
Isn't there sometimes where you like add electrons?
When you're adding your oxidation and reduction reactions, you want to make sure your electrons cancel out. But when you're just doing a half reaction, you should have electrons in there because we're changing an oxidation state. Does that make sense?
Can you rewrite that like reaction that it was oxidation? Like
Yeah, you would just flip your reactants and products basically.
so, like the arrow just go over that.
Yeah. Right, a little bit about structure because we did have a short unit on it. So remember we talked about a bunch of different types of isomers. Geometric isomers are the ones that we can visually see. So those are when we have cis and trans versus face and mer. Then we have optical isomers. So optical isomers are typically chiral. So these are non-superimposable mirror images of each other. And then linkage isomers are quite literally when we're just changing the way some ligands are bound to it. So here they give us this triamine triiodo iridium complex. What type of isomer do we think this is? Yeah, it's a face-mer isomer. So the way we know I like to think of the face-mer isomers. This is the face one. Face ones are triangles. It's a little triangle with my 3 nitrogen or my amines. Or you can think of a triangle down here, however you'd like it. That's like a square that I drew, but you know, it's like a triangle if you're like looking at it like down from the corner. That's how I think of it. And then the mer one would be if I have like a ligand here, and a ligand here, they'd have to be separated, like all throughout the compound, kind of like a plane almost.
If it was linked or optical, they have to be true.
Yes, yeah. Well, optical, they could give you 1 because optical includes chiral compounds. So as long as it's a non-superimposable image, or like you could flip it around a thing and it's like your hand, then it would be an optical isomer. Linkage, yeah. Linkage, coordination, hydration, they would have to give you 2 things so you could compare them. So yeah, this is face. Down here is mer. But yeah, I think of it because it makes like a triangle face when you look at it in the corner. Well, mer makes like a plane almost if I connect all my ligands. Any questions on that? Cool. All right. Some questions about tungsten 0 hexacarbonyl. What does that 0 in parentheses mean? Yeah, that's it. Just means, has a 0 oxidation state. And what is carbonyl? What type of ligand is that? CO. What does hexacarbonyl mean? How many do I have? 6. Awesome, I love that. So the first problem then is WCO6. Now, does carbonyl have any charge on it? I guess that's a hard question. It does have a charge, but it is neutral. So carbonyl. That's it. So it's neutral, but the carbon's negatively charged technically, and the oxygen's positive. But the overall charge is 0.
So let's say I was taking this exam and this was a question and I didn't know which one was tungsten. Is that a question that you would answer for me?
No.
Okay.
As much as I would love to, I would not be able to.
Alright. You don't give us the periodic table with the names.
We don't, but we also expect a certain, like, we talk about tungsten in this class frequently enough that it should be known, and we expect, like, Chem 112 people to know, like, the thing for, like, technetium. So,
For what?
technetium, TH, or TC, actually, sorry, my bad, TC. So, no, but I would say do your best and smile.
Like, if I didn't know it, and I wrote, like, the whole, if I wrote...
You'd only lose points at the first part. Only at the first part.
Okay.
Remember, we don't propagate error. If you make a mistake at one part and you answer the next parts based off your mistake, you will get points if your answers are correct based off your mistake. So, like, exactly. Say you said the other problem, like,
Just write it in.
say you said the other problem, like one of the ones I was asking about, like the tetrahedral or square planar. Say you switch them, and then you drew the right electron, like, D-splitting diagram for the tetrahedral. You'd only lose a point for mislabeling the shape, but not any points for the actual diagram, because you understand the concept that that diagram goes with that shape, and that's what we're testing for. So yeah, don't stress out if you don't know one part of a question. Do your best and just continuing answering how you would answer it regularly. All right, so we have tungsten, carbonyl. It wants us now to do the CFSE. So when we're doing CFSE, that's, remember that formula where we have 0.4 times our T2G electrons minus 0.6 times our EG electrons. And that's with delta O followed by it. So first we need to figure out the oxidation state of tungsten. Well, it tells us it's 0. So our electron configuration then is 6s2, 4f14, and 5d4. We're just looking at D splitting, so we don't really care about those F and S electrons. We're just going to look at our D electrons. So since I have 4 D electrons, yeah.
Sorry, Dr. Lori did just email me back. It's in
75 Willard. There we go, guys. I'll write that up here. Is that in the basement?
Yeah.
That's so sad.
It's really depressing down there. It's a nice way.
Last semester it was like all the way down in Stidle. It was a nice building. All right. All right. Anyways, so we're back to our tungsten. Tungsten is a 5d4. So since we're a d4, we have to take into account spin states. What do we think tungsten's going to be? High spin or low spin? What type of ligand does it have? So strong field is going to be low spin. So we have a strong field ligand. So it is low spin. And since it's low spin, how does our delta O compare to our pairing energy? Is delta O larger or smaller than our pairing energy? And remember, delta O is the space between these two orbitals. Yeah, delta O is very large. This is why it's low spin, because it's easier to pair an electron So now we'll go ahead and fill in the electrons. We have 1, 2, 3, and since we said it's low spin, we stay down in our T2G orbitals. When we're calculating our CFSE, all these are in our triply degenerate orbitals, so we'll just do 4 times 0.4 delta O, and this gives us 1.6 delta O, but it tells us to include pairing energy if necessary. So the way that we're going to analyze if something needs to have pairing energy included is we're going to look at it as if all our orbitals were degenerate. So if I had 5 degenerate orbitals, and this was D4, I'd have 1, 2, 3, 4. Nothing is paired. But when I compare it to this scenario, I have one thing paired. So that's going to be minus 1p. Does this make sense? So when we're including our pairing energy in our CFSE, we compare it to if all the orbitals were degenerate, does it have the same amount of pairing? And if it doesn't, we have to add a pairing or subtract a pairing energy in this case. Yes?
So theoretically, if it was a weak field ligand that was like DA, whatever, so that they're all empty, like they're all not paired, would you not have to write the same?
Yeah, so technically you could also look at this. I was taught to look at it as if it was all high spin and then compare that and then do the pairing energy, because it would be the same thing as if they were all degenerate, because you're filling them all in one way. So when we're talking about low spin complexes, they are the only ones that matter. High spin complexes, they're not going to have a pairing energy included because they're always going to match if all of them were degenerate. Yes.
Is that a different equation than like the 2/3?
No, it's the same one. It's the 1 2/5 and 3/5. So I use decimals. You can use decimals or fractions. There is not a right or wrong way to do it. I prefer decimals, but if you like fractions, by all means, continue your fractions. All right, any other questions on that one? All right, what type of ligand is carbonyl? Is it a pi donor or a pi acceptor? Pi acceptor. So typically, the way I've learned to remember this is when I've thought about my spectrochemical series, my weak field ligands are typically sigma donors only. Then my middle field ligands are sigma donors and pi donors. And my strong field ligands are sigma donors and pi acceptors. Now this isn't always the case, there's some mixing around in the series, but I know that whatever my strong field ligands are, if they can pi back bond, that means they're pi acceptors. They're accepting electrons from our metal center. Everything is a sigma donor. That's why sigma donor is not listed here, because it would have also been the answer. Everything is a sigma donor. But carbonyl and cyanide are pi acceptors as well. Yes.
What's an example of a sigma donor?
Chlorine or halogens. All right, so now we're gonna Was there another question? No? Okay. Now it just wants us to explain why carbonyl is a strong field ligand. So I kind of went over why that was in that last little spiel. So CO is both a sigma donor and pi acceptor. So it can participate in pi back bonding. Which occurs between a filled d orbital this is typically dxy, but I don't think we need to know that deep in this class. And an empty pi star orbital. Now, if you wanted to add a little visual description to support your answer, I always support adding a description because that's the best thing. We would have our metal d orbital. So typically, like I said, this is the dxy orbital, or one of our d orbitals that looks like a flower. So this is our metal. And then I drew the p orbital a little bit distorted because that's how it would be. That's why this interaction happens. But we would have our p orbital of our carbon. This is the carbon p orbital, not the oxygen, because we're donating into the empty pi star of our carbons. And it's donating electron density. It goes metal to ligand, not ligand to metal. Our ligand is a pi acceptor. So this is our ligand. Any questions on that one? Remember, pi back bonding, important. Carbonyl cyanide between metal d orbital, empty pi star orbital. Diagram looks kind of like that. All right, now we have a reaction question. This one's a pretty basic one where it's just 2 steps. In the first step, what we see is we're losing a cyclohexane, and we're getting this 2 coordinated, I guess technically 5 coordinated because it's technically bonded to many things. But how many things are we losing from 1 to 2? How many ligands disappear? 2. Does our oxidation state change? I guess that's kind of hard to answer here because it doesn't show you the charges, so I won't ask that. But when we lose 2 things, what do we usually call that? Reductive elimination. Reductive elimination also corresponds to the change in coordination number as well as the change in oxidation state. Now in the second step, what we notice is now we're gaining things. What do we gain here? Benzene and hydrogen. We gain 2 things, so what do we think this is? Oxidative addition. So oxidative addition, again, we're going to see a change in coordination number. Our coordination number is going to increase. We're also going to see a change in oxidation state. Important things, yes.
That's kind of a lot. You kind of give like a brief explanation of all the other things we did.
That is a lot. We can come back to that if we have time at the end. Is that okay?
Yep.
All right. Were there any other questions on this one? Alrighty. So now we're talking about the base strength of ammonia and how it's going to vary depending on what solvent it is in. When it's in water, it's going to have a different strength than when it's in acetic acid. So here it wants us to explain these reactions between our solvent and our solute, which is our ammonia. So the first thing I'm going to do is just draw the reactions between the 2. So first I have NH3 aqueous plus H2O liquid. And this is going to form NH4 plus OH minus. And then in the second one, I have NH3 aqueous plus CH3 COOH liquid. Now, which one of these solutions do you think Ammonia is going to act like a stronger base. In the acid, yeah. It's going to act like a stronger base in the acid. So what we'll notice is equilibrium is shifted depending on what solvent we're in. So when we're in water, ammonia behaves as a weak base. However, when we run it in acetic acid, ammonia acts as a stronger base because now we're reacting it with an acid. It's more of a neutralization reaction. So that's also why the equilibrium arrow up top is drawn much larger than the one on the bottom. Like, it's a big one in the forward direction and a tiny one in the reverse direction. And like I said, equilibrium becomes more shifted towards our product. So we have a higher KB in this case when we're running it in something like acetic acid. So what we can see from this is that the strength of our base is leveled based off our solvent that we're putting it in. And same thing for our acid. The strength of an acid is leveled by the solvent that we have put it in. All right, any questions on that? This is just like another discrimination effect solvent leveling type of question, but with just one thing in different solvents. All right. Metal carbides and nitrides adhere to which crystal structure type? We have something that's pretty ionic. So what do we think this is going to be? Think about the sizes of them. Think about how they like to coordinate to things, the properties of metal carbides and nitrides. What structure do you think they'd be similar to? When we're looking at zinc blende and quartzite, those are zinc sulfides. We have nickel arsenide, sodium chloride, and rutile. It's sodium chloride. I don't really have a great explanation for this. That's the shape they like to be in. We have a high charge. They like to be in a coordination number of 6. They like to have a pretty close packed structure. I'll ask a follow-up question. Why are zinc blende and quartzite both zinc sulfide? Do they have different structures? Yeah, what's zinc blende? What about quartzite? Which one do you think is the more common type? FCC. I don't know if we talked about that one too much, but FCC is more common than the HCP version. HCP version you need like high pressure scenarios for. But yeah, I would say some crystal type or structure type questions kind of come off as trivia. So just review them real quick. Make sure you know your structure types. Make sure that you have a kind of basic understanding of like the ones that we spent a lot of time talking about. Any questions? I also can scroll up if you want to see anything else. Yes.
Could you look for the difference between N-type and P-type for
Yeah. So let me pull up a periodic table. I'm going to stop.